Hello, everyone, and thank you for joining us today. Welcome to another session of Steam Management's webinar series. Today, we'll be discussing carbon reduction opportunities for industrial steam systems. This presentation will take a practical look at ways facilities can improve efficiency and reduce emissions through steam system improvements, controls upgrades, heat recovery, cogeneration, electrification, and emerging technologies. Leading today's discussion is Chase Bean. He's Steam Management's Vice President of Revenue and Engineering. Chase leads the SMI engineering team and has over 18 years of experience in the energy sector, spanning engineering, project management, and business development. During the presentation, you're welcome to ask questions in the chat at any time, but we'll also leave time at the end for Q&A. You can also get a PDH certificate following the session just by emailing Chase at that email, and we'll show his email again at the end of the presentation. Thanks again for joining today's webinar, and with that, I'll hand it over to Chase to get started.
Yeah, thanks, Ashley.
I did forget to say that we will also launch polls throughout, so keep an eye out for those.
Yeah, thanks, Ashley, and thanks everybody for joining. We are Steam Management. We're a trusted partner for steam system solutions. So we support facilities nationwide with full cycle steam system solutions from assessment to implementation. These solutions drive measurable savings, energy savings, and reliability improvements. And we are in a variety of facility types, basically anywhere that has steam. We will have something to offer. So yeah, let's get started. First, our disclaimer: this presentation is intended for technical and education purposes only. It is designed to provide general information about different technologies, their applications, and their operational principles. We are not affiliated with or representing any specific equipment manufacturer, distributor, or product line. The inclusion of any specific products or features is solely to illustrate concepts and should not be interpreted as an endorsement or promotion. Attendees are encouraged to consult with SMI when selecting equipment to meet their specific needs. As an overview today, we're going to talk about steam use in industry, carbon reduction approach, typical practical efficiency measures, a little bit on cogeneration and combined heat and power plants, some other current boiler house options and future boiler house options, and then we'll conclude. So first, steam use in industry. Industrial steam is firmly embedded across major production sectors. We'll talk about why in a minute. Some of these sectors are food and beverage, chemical manufacturing, pulp, paper, and forest products, pharmaceuticals, refining, and petrochemical, and hospitals and campuses. But one that I would point out also is just general manufacturing. So we go to a variety of manufacturing facilities, and there's all sorts of creative ways that they are using steam for process heat, forming, drying, curing, cleaning, humidification. It's really a key part of the industrial landscape. Why does steam remain common? Basically because it provides a high temperature thermal energy reliably. So the technical advantages are its high heat transfer rate through latent heat. That's through the phase change from steam to condensate. Stable temperatures at any given pressure, so it's predictable properties. Easy central generation and distribution. It's useful for batch and continuous processes. Can serve process, building, sterilization, and humidification loads from one system. And it's a mature technology and maintenance practices. It's also abundant and ecologically friendly as a medium. It's just water, right? So the carbon impact of steam is from generating it with fossil fuels, which we'll talk about more later. Some business advantages: production teams understand the technology. Existing plants are already piped for steam. Steam is easily integrated into many industrial operating environments. There's low risk of product contamination, again, because you're using water. Central plants can be maintained without touching every end user, and the reliability and uptime are often more important than simple efficiency. Where steam-related carbon comes from. So fuel obviously is your first source of carbon emissions, and different fuels have different emission rates. But then it's how efficient is your boiler, how efficient is your distribution, and where are those losses occurring? how efficient are the end users, how well are you returning condensate, and then especially for larger solid fuel boilers, what is the electrical load of the system? And so all those things can be evaluated for efficiency improvement. Some challenges when you're decarbonizing steam, it's hard to replace for high temperature heat. Steam is still one of the best media for high temperature heat. I would say some of your only other options are maybe thermal fluids, high temperature thermal fluids, or direct firing. And that's just not an option for many facilities. Many industrial processes need heat that is difficult to electrify directly. Steam provides a large thermal capacity. It's very controllable, and there's distribution flexibility. Existing plants are built around steam pressure, temperature, and reliability. And low carbon alternatives often require major changes to generation, distribution, or end users. The problem is that most steams still rely on carbon-based fuels today. So that's the problem from a decarbonization standpoint.
I'm going to launch our first poll, which is, which of these most often makes steam decarbonization difficult at your facility or project site?
We've got incomplete steam system documentation or data. It's kind of leading. It looks like it's been taken over by budget payback or competing capital priorities. That one seems to be taking the lead. Interesting. So practical carbon reduction hierarchy. So I say first you're going to assess your system. You're going to develop a heat and mass balance, survey and test your traps, audit your insulation, install meters and monitoring for more visibility, and develop operating profiles, load cases, all the things that you can do to evaluate the performance. Then I have repair and optimize as like 2A and 2B because they're both kind of important as first implementation steps. Repair steam traps, leaks, installation gaps, condensate issues and controls, tune combustion, sequence boilers, or optimize sequencing, stabilize pressure, and then look at recovery options. So you could capture additional condensate by reconfiguring return systems, capturing flash steam, blowdown heat recovery, additional stack heat recovery. All of those kind of require some projects, right? So that's kind of why that's number 3. And then modernize, and then you're talking about actually replacing equipment, upgrading end users, boilers, controls, implementing advanced monitoring systems, and other replacing other boiler plant assets. Baseline data required when you're doing an assessment. So far as steam side, look for boiler fuel consumption and steam production, header pressures and operating schedules, annual, monthly, and hourly load profiles or trend data can give you a lot of this information. Trap population status and failure history, like a steam trap audit report is a really good indicator of a lot of characteristics of a steam system. Condensate return percentage and temperature, blowdown rates and feed water temperatures, segment flows and pressure drops, and just some of the key data points that are helpful. And then on the business side, obviously you want electric rates and demand charges, fuel rates and escalation assumptions, required redundancy and outage constraints, production forecasts and planned capital costs, and maintenance staffing capability. Some typical assessments say deliverables. You want to get a opportunity report. I think a good assessment is going to have a heat and mass balance with load cases in many scenarios. You want a trap survey and line-by-line application schedule, condensate and heat recovery opportunities, boiler plant efficiency recommendations, generation equipment assessments, order of magnitude budget ranges is important, implementation, phasing, and outage considerations, and carbon, energy, water, and operating cost impacts. The study should connect field findings to capital planning. What should be repaired now, what should be designed next, and what should be monitored for future maintenance, insight, and replacement decisions. Here's an example of a heat and mass balance where you're taking all the flows in the system, or at least the important flows as far as evaluation, and you're balancing all of those out to really get more insight into what's going on at key points in the system.
All right, I'm going to launch another poll. What do you think is the hardest part of evaluating steam system improvements?
I got 9 responses. It's saying getting accurate steam flow and load data. I would agree with that. That's what I voted for. All right, now we'll talk about some typical practical efficiency measures. Some of these I've talked about in other webinars, but they just can't be overstated. The first of which is steam trap survey and repairs. This is probably the most direct path from analyzing a field condition to avoiding fuel consumption or decarbonization. So you're going to survey and tag traps, test traps for operation and document status, identify failed open, failed closed, leaking, and block traps, review strainers, isolation valves, check valves, blowdown valves, bypasses, and drip legs. You're going to prioritize repairs by pressure, size, operating hours, and access if you're not going to be able to repair all of the failed traps. And then you're going to repair or replace traps and failed station components. The carbon reduction reliability value, failed open traps waste live steam continuously. And traps are generally designed to fail open so that the condensate still can get out of the system to avoid hazardous conditions and so the equipment can still operate properly. So it is just a total waste. It's just blowing steam out of a hole. Generally, when they fail, they can fail closed, which can create cold equipment water hammer risk. That's usually from some sort of plugging of the hole of the trap or the orifice. Correct trap selection improves drainage and process stability. You want to repair trap, or a repair program should be repeated regularly, and trap monitoring improves visibility into maintenance needs and urgency, which we'll talk about on the next slide. So here's some examples of different trap monitors. Basically, when you monitor steam traps, you're going to want to prioritize critical, inaccessible, and high loss traps. So the best fit is traps with high run hours, high pressure, and large orifice sizes. You're going to want to use the monitoring system to continuously identify failed traps, but you're going to want to pair that with prompt action. So the monitoring system gives you good insight. It doesn't prevent trap failures, and it certainly doesn't address them. So it has to be paired with action to get the benefit out of it. So the best case is a recurring maintenance program where trap monitoring data leads to prompt work orders and measured avoided losses. Repairing steam leaks. Here are some common leak points. I won't read all of these. And typical corrective work. Basically repairing or tightening or replacing, components that are leaking. You also want to evaluate why those components led to leaking. So there's some items there like correcting supports and anchors, improving access to those components for ongoing maintenance and that type of thing. Installation of piping, valves, and fittings. Missing or damaged installation is common on active steam systems. Valves, flanges, strainers, and fittings are often left bare, as you can see in the photo here. So this is the top photo is before installation, bottom is after installation of the same. This is the same section, although the coloring is a little bit different. You can see there's going to be a lot of energy conserved here, but this was insulated. This isn't damaged installation. They just left this off, right? So removable covers reduce heat loss while still allowing maintenance access. Insulation improves efficiency, safety, and steam quality. So any energy lost in the steam system is basically going to generate condensate, and that's going to affect your steam quality. And when we say steam quality, we mean dryness of steam. So the more water that drops out of the steam, the worse the steam quality is going to be. The more that water is going to pool up in the bottom of pipes and in drip legs and get entrained in the steam as it's traveling through. Steam systems are hot compared to other utility systems, so installation paybacks are fast. So if you ever evaluate like a chilled water system, a steam insulating a steam system is going to be a much faster payback than something like that. For example, condensate return improvement. Some common scope items here are replacing failed condensate piping, installing, repairing, or replacing receiver and pump packages, correcting venting, net positive suction head, and pump control issues, addressing water hammer and lifting problems, and adding flow, temperature, and conductivity monitoring. The benefits of improving your condensate return: you're going to get you're going to get a lower makeup water requirement, and that is from less steam heating required for the feed water. The benefits of that are of requiring less makeup water is now you've conserved some heat, so you have less steam heating required for your feed water because you're returning more hot condensate instead of cold makeup water. You're going to have lower chemical consumption because it's now less makeup water to be treated, and you're going to have lower blowdown requirement, which we'll talk about in a bit. But makeup water is where impurities are introduced to the system, and so the more makeup water you have, the more blowdown you have required, which is a waste, and we'll talk about that in a minute. You're also going to just generally improve your boiler plant stability. Flash steam recovery. So when I talk about there's a couple different ways to recover flash steam, but or energy from flash steam. But one is to reconfigure a system with a pressurized condensate tank. So if you take, like, say you have a 100-pound steam system, you have the condensate's coming out at 100-pound saturation temperature. When that gets to your atmospheric tank, it's going to flash off a significant amount of steam, somewhere, I think, for 100 pounds, like 12, 13%, something like that. If you can take that to a pressurized condensate tank and let it flash at, say, 10 pounds, and then capture that steam and reuse that in a low pressure steam system, now the condensate coming out of that flash tank is now only going from 10 to atmospheric, and there can be a significant reduction in flash steam losses, which is going to improve your condensate return as well. And there's a good savings benefit. The downside is you do kind of have to have a low pressure steam user that you can route it to, but that is a common efficiency scope. Blowdown controls and heat recovery. So some scope options here are to automate surface blowdown control. For this, we are talking about surface blowdown. So that is a point at the surface level of the boiler water. Those are steam drums represented there, here, and here. But surface blowdown continuously removes total dissolved solids from the boiler water surface to control concentration, reduce carryover risk and waterside fouling, and maintain steam quality. So one scope option is to automate that process. More manual processes tend to have to do a conservative amount of flow in order to maintain the appropriate levels, TDS levels in the boiler. So you're having excess blowdown, which is just wasted heat, right? Like you're heating feed water all the way up to saturation temperature, and then you're just blowing it down the drain. So it's just a total waste, but is necessary. So minimizing that is an efficiency scope in itself, but also that's a waste heat stream. So you can capture that in a blowdown heat recovery system, which is basically like a flash tank and heat recovery package where you preheat makeup water. That's probably the most common application for the heating. You're going to capture some flash steam and use that in your deaerator, and then you're going to mitigate tempering water requirements at drain, which we'll talk about in a minute. But the value drivers for this scope are a higher operating pressure of the boiler. That means the blowdown stream is going to have more energy in it. the rate of the blowdown, which is driven by your makeup water rate. As I mentioned, makeup water introduces dissolved solids that requires more blowdown. If that makeup water is poorer quality and it's going to have more impurities in it, then you're going to increase your blowdown requirement. And then, as I mentioned, manual blowdown practices are going to have, increase the amount of blowdown you have. And then once you determine your blowdown rate, that's generally expressed as a percentage of steam or feed water. Obviously, the larger the boiler is, say if the blowdown rate is 3%, the larger the boiler is, the higher that blowdown stream energy content is. And then, like any scopes, your fuel, water, and water treatment costs are going to drive the value of that energy and water that you're trying to save. The ability to reuse heat, flash steam, and mitigate tempering water are important, which I'll talk about here. So in this scope, you have the surface blowdown is coming to a heat recovery system. In this system, first, the blowdown is going to flash off. That steam flashes off clean and can be reused in the deaerator. So it's going to offset some of the steam requirement here. Then there may be some, there's going to be some sort of heat exchanger, either internal to the flash tank or downstream. But you're going to typically use that to preheat makeup water. And then last but not least, typically this blowdown is going to come into the bottom blowdown tank, flash off, and this tank's going to sit around 212 plus degrees. Most facilities have sewer temperature limits where the drain of that has to be tempered down to 140 degrees to not damage their drainage system or sewer system. So there is typically a tempering water valve here that is a significant amount of water used just to cool this down. With these heat recovery systems, this exit temperature is often going to be down to 90, 100, 110 degrees, but well below that sewer limit. And so you're mitigating this tempering water requirement. I have a whole presentation on this scope. If you're interested, you can find that on steammgt.com/webinars. Economizers and stack heat recovery. So these are best for, I should say they recover sensible heat from flue gas and transfer it to the boiler feed water or makeup water or other process. They're best for high run hour boilers with stable stack temperatures. Typical application is feed water. Combustion air preheaters are common for larger boilers. The design for a traditional economizer must consider the flue gas dew point. So you don't want to unintentionally turn your boiler into a condensing boiler. And then condensing economizers typically need low temperature, another low temperature process, or possibly preheating makeup water into the system if there's a significant makeup water stream. Some rules of thumb is a 1% efficiency increase per 11 degrees of feed water temperature increase. An economizer that recovers 5% of boiler input should easily have a 2-year payback in a year-round application. So he's going to have very good paybacks if the conditions are right. And then for combustion air preheaters, there's a 0.5% efficiency increase per 20 degrees of combustion air temperature increase. Another interesting scope, which I would like to see somebody do, is to pull you duct the inlet of your combustion air up to the top of the boiler room where the heat is just in the room is stratified up there, and pull that into the boiler for a hotter combustion air intake. I think that's an interesting and simple scope. Here's the boiler with an economizer. Here's one without. These are actually in the same boiler room, and as you can imagine, the one with the economizer is the primary boiler, and the other one is the backup boiler, and that's why they didn't invest in an economizer. Another scope is burner controls and boiler sequencing. So as far as burner controls, upgrading a system like this, where it's called single point actuation. It also is sometimes called jack shaft controls, but it's basically a single electric actuator is modulating this shaft, which is connected to the gas valve, the air dampers, and in this case, the fuel oil valve, all by linkages. the combustion is tuned on this boiler by adjusting these linkages, and it's kind of a manual process. Takes a little bit of expertise, but it is difficult to maintain. It's difficult to tune across all firing ranges and optimize for both fuels. And it quickly gets out of tune as air conditions change from changing seasons. So it's generally recommended to be done quarterly, and that is not always done. Modern systems have, especially like an O2 trim system, which I think is very applicable for an industrial setting because you're usually going to have a larger boiler and you're going to be able to justify this. But it's basically you're going to read an O2 reading in the stack. You're going to have parallel controls of fuel and air, and you're going to modulate those to optimize combustion. In this case, they have a VFD on the fan as well, and so you're going to get some electrical savings from the VFD. But that's the idea. At a minimum, modern burners and boilers are going to have parallel positioning, which is at least independent actuation of fuel and air, and maybe that's just run off a control curve and not actually reading O2. And then some other control upgrades are improvement of boiler sequencing and lead lag logic. And also you could conduct a turn down the fire hold review to evaluate cycling issues. Steam pressure reduction reset. Basically the idea here is steam systems are best operated at their lowest pressure required. So you want to be high enough to serve all of your loads and not cause any issues, but there's no benefit of operating higher than necessary. And the lower the pressure of the steam system, the less the losses are. So you reduce radiation losses, you reduce the force to drive flow through leak points like traps or any leaks to atmosphere. Now you have less upstream pressure to, push steam out of those holes. There's going to be similar. There's going to be less flash steam from condensate. Well, not similarly. I'm actually saying there you're now having less flash steam from a higher pressure condensate because your condensate is now coming out at a lower temperature. So you're going to mitigate flash steam a little bit. You're going to reduce your feed water pump power in the case of high side pressure reduction, where you're reducing your pressure in the boilers. Now those feed water pumps have less pressure to pump against, and there's an electrical savings there. Reduced pressure in the boilers also leads to less loss from boiler blowdown, just because even if you have the exact same blowdown flow, now that flow has less energy in it. And so that's mitigates that loss somewhat. And then you're going to improve your combustion efficiency because you're going to increase the differential between your boiler water, which is now at a lower temperature, and your products of combustion. PRV station optimization. For these, you want to survey these and document inlet pressures, outlet pressures, set points, flow, redundancy, configuration, and safety relief valve arrangements. You want to correct hunting, undersized bypasses, failed pilots, plug sensing lines, and poor condensate removal. You want to review whether parallel PRVs or stage control would improve stability. You want to consider digital pressure reducing valves to optimize downstream pressures for demand. That's a good efficiency scope. Basically, having a digital control valve control the downstream pressure based on the required demand. And then for large steady pressure drops, you want to screen for a back pressure turbine potential. That is replacing a PRV with a back pressure turbine, so the steam, you're generating steam at a high pressure, you're sending it through a PRV. The exhaust of the turbine is coming out at still some pressure, 50 pounds, 10 pounds, whatever it is, and then that's feeding your 50 pound, 10 pound, whatever it is system that you have instead of having a PRV. So that's a really good scope if the conditions are conducive. Steam metering and dashboards. I won't read all these, but there's some notable data points and output metrics here. But metering gives the steam system visibility. You don't need to meter every line, but you do need enough data to understand how much steam you're making, how much fuel and makeup water it takes, where the steam is going, and how much condensate is coming back. And once that data is tied into a dashboard, you can track efficiency, steam costs, and emissions over time instead of relying on spot testing or assessments or operator experience for visibility in your system. So just like other utility systems, just that visibility can be crucial to manage the system. Now we'll talk about.
Sorry, Chase, we
Sure.
have another poll.
Yeah.
Which practical steam improvement would be most valuable at your facility or project site?
Okay. The answers are kind of as expected, although this is going to be custom for different systems deficiencies. I did mention earlier, steam traps are kind of your most direct way to improving efficiency, but all of these other things are good opportunities as well. Interesting. Thanks, everybody. The next section is we're talking about cogeneration or combined heat and power systems. So just kind of some high-level overviews of what's out there in regards to these. But combined heat and power is most compelling when recovered heat is consistently useful. So for anybody who doesn't know, we're talking about a system that generates thermal energy and electrical energy, and that's kind of the idea of cogeneration or combined heat and power. Some major considerations are the fuel input. So for, if you're generating steam and then using steam to generate power, you can use any fuels that are common in, high pressure steam boilers. You want to consider your prime mover. That's your electricity generator generally. That could be a gas turbine. It could be a reciprocating engine, or it could be a steam turbine combined with a boiler, obviously. Power, what is the on-site power requirement and the benefit of on-site electrical generation generally? It could be the benefit of, having avoiding interruption of production. What is the heat recovery method? And then what is the useful thermal, or what is the useful thermal energy potential? I think I saw a comment. Are industrial processes ever reviewed to determine if the highest pressure steam is even required? For example, plant outputs 250 psi, but a close review reveals that they could run at 200 psi and still service the max loads. Yeah, that's a great point. And yes, I would say this is we do these analyses. We call it a pressure reduction assessment. And there's a whole list of potential impacts that could be problematic that need to be evaluated. And there's a whole list of potential savings points. So it's even the savings is not that straightforward, but you do want to get an understanding of what the benefit is. And we have another webinar on pressure reduction that you could check out if you're interested in more. That should be on our website also. But yes, that is done, and it's a good scope. Okay, so for CHP, we're talking about a gas turbine. When I think of this, it's usually paired with a heat recovery steam generator on the back end. These are basically, if you look at this transition duct here, this is the exhaust of a gas turbine, and that exhaust comes out hot enough to generate, decent pressure steam. And then this is all heat exchange area as that flows, across the boiler and then eventually up the stack. But so you're generating power with the gas turbine, and then you're generating steam with the heat recovery steam generator, which people call HRSGs for short. You can use that steam for process loads or any kind of thermal loads, but also you could just send it to another steam turbine and generate more power and just increase the electricity output. But some key features here, captures high temperature exhaust from gas turbine, produces steam without direct boiler firing. Although I will say it's common to have duct burners in this section to supplement heat when the gas turbine is not, it doesn't have as much load, so you can still get your steam required from your HRSG. Best fit applications is facilities with steady steam demand and desire for on-site power generation. It's common in campus steam systems, hospitals, refineries, utility plants, and industrial sites. And it's good for sites seeking lower fuel use and emissions, as well as sites with a low gas cost, because that's your fuel you're burning, and higher electric costs, and they get the benefit of the power generation. Reciprocating engine, combined heat and power. I'll mention this. This is not as common in steam systems, but this is basically like a diesel engine or a gas engine. And then you're recovering jacket water heat, exhaust gas heat, oil cooler heat, after cooler heat. Possible to generate steam. I would say most of these are going to be for hot water systems. They usually the temperatures you're able to recover from these are a little bit lower. So it's going to be, low pressure steam or hot water thermal energy. Probably the most traditional arrangement for industrial sites is a boiler and steam turbine combo. This is what I think of when somebody mentions cogeneration. It's the first thing I think of anyway. Like I said, you can use basically all the common fuels to generate the high pressure steam. Then you're going to send that through a back pressure turbine. You may have a combination of back pressure turbines for different lower pressure steam systems. If it's a big complicated facility, you may still have PRVs on the side. Whatever the case may be, these can also often be pretty interesting, complicated configurations. But basically, you send the steam through a back pressure turbine. The exhaust of that turbine still has some pressure. So say you send a 600-pound steam into the turbine, it comes out of the back end at 100 pounds, and you have a 100-pound steam system to utilize that steam. And so that's the cogeneration there, as compared to just generating steam into like a condensing turbine and trying to get all the power out of it. The carbon case here depends on the boiler fuel, grid emissions, operating hours, and whether heat is fully used. Question here: if the heat recovery is at hot water temperature, why not preheat the steam boiler makeup water? Yeah, that's a possible application. I've had the same thought for industrial heat pumps, which talk about next, because you could capture waste heat out of the flue gas stream of the boiler and then use it to preheat makeup water. But you'd have to have the right conditions for that, I guess. Thanks, Keith. Some CHP benefits. You're going to reduce purchased electricity when operating. You can improve the total fuel utilization when recovered heat is fully used. It may support critical operation during grid outages if configured for islanding, and that's a common thing that you'll see. Is facilities will invest in their own power island so that they don't have interruptions in production. It can stabilize power cost exposure for large electrical users and can support future plant modernization when integrated with boilers and controls. Somebody said, does steam leave the steam turbine as superheated or saturated after a back pressure turbine? I think it still has some superheat generally. I don't think it condenses. I don't think it gets all the way to saturation, but I don't remember the answer to that, honestly. I believe it usually still has some superheating. I guess it depends how it's designed. Okay, some other current boiler house options. First is electric boiler. So if you're talking about decarbonization, this seems like an obvious solution, and it could be, I guess. They're technically simple, but commercially and electrically complex. So the strengths here, you got zero on-site combustion emissions, fast response, and simple steam output. It's useful for peaking, backup, or hybrid operation, and can align with low carbon electricity procurement. Can support demand response in some markets. The constraints here is a large electrical service requirement. So this particular electric boiler in the photo was told by the plant that it took more energy than the whole rest of the plant combined when operated. Demand charges and operating cost exposure. So we've run numbers on some of these. Generally speaking, I would say, and obviously this depends on utility rates, but it can cost around 4 times as much for the electricity to run the boiler as compared to gas for a comparable gas boiler. The carbon benefit depends on the electricity source. So if you're using electricity from a coal boiler, you're not really doing much because it's going to be generating that heat in the coal boiler to generate electricity to then generate heat is more carbon emissions than burning gas directly at the boiler. And it may require backup combustion capacity anyway, which we'll talk more about. Biomass or alternative fuel boilers. Some common fuel options are wood waste, bark, chips, and pellets, agricultural residues and food processing byproducts, biogas, landfill gas, and digester gases, bio oil or renewable liquid fuels, waste-derived or industrial byproduct fuels. Some strengths here are it preserves a central steam plant model, can reduce natural gas dependence, can be a strong fit where local fuel stream exists. And you'll see this a lot where the manufacturer or the facility has biofuels as a byproduct of their process. So like very common in pulp and paper or agricultural facilities. It may improve the resilience with on-site fuel storage. So they were talking about being able to store a pile of biomass, and so you're not dependent on grid supply for electricity or natural gas supply consistently. You can stock your fuel. It can support long-term carbon reduction plans, and a lot of these are considered to be carbon neutral or sustainable fuels, even though they're still carbon emissions. Some constraints: the fuel quality and moisture can vary. It requires handling, storage, and ash management. Those are complicated systems with, significant electrical loads. Emissions controls and permitting can be significant, and larger footprint and higher O&M burden for these large boilers. Economics depend on reliable long-term fuel supply as well. So, for example, say you're using TDF, it's an alternative fuel, maybe not a carbon neutral fuel, but like tire derived fuel. Are you going to be able to get that consistently for the next 10 years? So you have to really evaluate where the fuel source is coming from in order to invest in installing a huge tire burning boiler, right? Hybrid gas and electric boilers, I would say these are becoming pretty common for moderate sized boilers in Europe. Basically, you have the ability to burn gas to generate heat in the boiler and use electricity. And so you can maintain conventional steam service while adding electric flexibility. Can operate gas only, electric only, or combined gas and electric. It reduces the risk compared with full electrification because you still have the option to burn gas. And I think it could be a useful bridge option for phased boiler house modernization. Some constraints: electrical service may limit electrical contribution or electric contribution. Demand charges can offset fuel savings. Controls and operating strategy are more complex. The carbon benefit depends on the grid mix and dispatch profile. There's a higher first cost than just a standard gas-fired boiler, and they're still combustion-based unless you're operating fully electric. I will note some boiler manufacturers now are leaving a space for a future, immersion heating element for electrical support or electric steam production. So basically leaving the possibility to integrate that into the boiler down the line. Now we're going to future boiler house options. So this is actually a picture of the Savannah plant, Riverside district, where they converted a power plant into a commercial space, but it's a pretty cool area. But anyway, it looks like a futurized power plant to me. One option that's kind of a buzzword lately is industrial heat pumps. So it's emerging electrification technology that can upgrade recovered heat into useful thermal energy, including steam in some applications. I would say for steam generation, often this is a lot of the designs are still dependent on a higher temperature heat source than just like ambient air. But it can recover energy from a warm waste heat stream and generate steam potentially. There's also designs that are kind of the lift is done in stages to get a higher temperature output. But if you have several loops, now you're starting to lose the efficiency. But it is an exciting technology, particularly for facilities with a lot of lower pressure steam use, hot water demands, and it could be a solution for a hybrid boiler house. I think this is going to grow as something you're seeing in industrial systems. Another one that's on the horizon is advanced small modular reactors for industrial cogeneration. I think this is a really interesting solution for the future. What small modular reactors are, they're basically smaller nuclear reactors compared with the utility scale units. They're designed as modular units that can be factory fabricated and then installed in the field. And basically, they produce thermal energy, which can become electricity, steam, or both. It's a potential fit for continuous baseload industrial energy demand, and why they matter for steam systems. So I'll get into this some on the next slide too, but it's a potential replacement for fossil boiler or CHP fuel input. So if you want to look at nuclear energy as carbon free, you could just completely decarbonize a large fossil fueled boiler plant, right? The strongest fit may be industrial cogen, not power only generation, basically because electric conversion is typically only 30 to 40% efficient in a nuclear plant. Direct steam or process heat can preserve more of the reactor's thermal output. Steam and power outputs trade off. They are planning to deploy these commercially in the early 2030s, which, not to stress anybody out, but that's not that far away. Broad industrial adoption is more likely later into the 2030s, but these will be here before you know it, particularly in larger central generation plants. And I've heard some military leaders talking about how these are going to be deployed at they're already planning to deploy these on military bases for central generation. So this is maybe the central plant of the future. And it's interesting because it's replacing all of the carbon emissions, but you can utilize the existing distribution system. Some math here of why I think it's interesting for industry. For a 100 megawatt reactor example, let's say your distribution system for your conversion to steam and your distribution system are 85% efficient. That means you're getting 85 megawatts thermal of useful heat out of it. If you go to power generation, you're getting 35 megawatts of electrical energy. And then if you were to go to power generation and then convert that back to heat for like a bunch of satellite electric heaters or users, now you're taking that 35 and multiplying it back by 85%, say, and only getting 29.8. So the best application, it could be argued for these, is a heating load. And like I mentioned with the coal boilers earlier, generating heat and keeping it as heat is more efficient than, going to heat and then power and then back to heat. Another one to mention is hydrogen. Hydrogen is complicated because it's energy intensive to produce green hydrogen. So kind of the opposite of what I was just saying, but generating renewable power to then use that power to generate hydrogen is kind of inefficient. It is related to small modular reactors though, because it's talked about as a potential way to keep those reactors base loaded. It's just generating hydrogen. Hydrogen is interesting in boilers because it's it's a combustion source, but the byproducts have no carbon in them, so it's just water basically that comes out of the process. So it's interesting, and it could be utilized in a lot of similar boilers as today. You're just changing out burners and things, but the storage and delivery are complex. The generation of it is difficult, and other issues as well. I do think if nuclear kind of takes off, I do think this might be something that plays in the landscape, though.
And
Oh,
I
go
just
ahead.
launched another poll. Which boiler house option seems most realistic for your facility or project types in the next 5 to 10 years? And when we wait for those answers to come in, here's a question from earlier. For existing plants that do not have full steam metering, what minimum metering package do you recommend to establish a credible baseline for steam savings, boiler efficiency, condensate recovery, and carbon reduction?
That's different for different plants. And I do have some suggestions on that slide. I think in my mind, I would probably see what's available and do a heat and mass balance and see what needs to be metered. And then those recommendations are often kind of custom site by site. But steam meters are always good. I would say steam meters and gas meters are if you were only going to do two. And then usually you have a makeup water meter just on your makeup water supply. But that's either measuring makeup water and condensate or both. So steam output, condensate return, makeup water, makeup water flow, and fuel, I would say, are probably the highest priorities, generally speaking. But yeah, that's kind of a case by case basis. Somebody says if the heat return is oh, I already answered that one. Does steam leave the steam turbine? We talked about that. Somebody said it's usually only saturated for condensing steam turbines and back pressure turbines. Okay, great. For large steam systems, do you recommend monitoring all steam traps or only critical and high loss traps? And what criteria do you normally use to decide which traps should be continuously monitored? That's a great question. All traps are good. I would say people don't typically monitor smaller traps like radiator traps on low pressure steam systems. Monitoring all traps is a good idea, but typically it's just a cost versus reward thing. So I guess the things that are considered are the things that drive savings from steam trap losses, which are going to prioritize higher pressure traps, higher run hour traps, and larger traps. Also, though, critical process traps. So if the facility has, say, a heat exchanger that's on a critical process and you really want to make sure that trap is functioning properly, that would be justification for monitoring. Some final takeaways: steam remains essential for many industrial plants. Carbon reduction approach should preserve productive steam service. Typical scopes provide the foundation for larger transitions. CHP cogen systems work when load profiles support them, and emerging technologies present interesting decarbonization solutions. Hybrid boiler houses are likely the near-term pathway, so some sort of combination of existing fossil fuel technologies and future technologies, or even more green current technologies. But the tagline here is better steam today, better generation choices tomorrow. And that's kind of how I see the future of steam. But yeah, that's it. Thanks everybody for joining. I will hang out for a bit and answer any more questions people post in the chat. You can email me at cbean@steammgt.com for your PDH credit certificate. I did mention a couple of other webinars because we kind of just scratched on the surface of some topics that we've done deeper dives into. And you can check those out at steammgt.com/webinars. And we also are available to do presentations for your teams if you think that's beneficial. I'll do one of these technical presentations for your team, so you can reach out to me about that. And yeah, we really appreciate everybody joining. And we hope to see you at the next one. And we'll hang out for a bit for any remaining questions. Keith asks, small modular reactors is a fascinating idea. However, who is responsible for safety security of the fuel waste reduction leaks if the tech is privately owned? I do not know the answer to that question, and I think that's why it's probably going to get rolled out in government facilities first. But I do think that will be, addressed in some kind of way. Yeah, somebody supplemented my answer. Prioritize monitoring traps with high pressure, high run hours, and largest and critical processes. Yep, that's what I said too. Can you talk about pros and cons of condensing boilers? Also, condensing boilers to me, those are typically for hydronic heaters. When you talk about a condensing steam boiler, you're usually talking about a condensing economizer that's heating up some external process. Condensate does not, and feed water does not come back at a low enough temperature to promote condensing of boiler flue gas, steam boiler flue gas generally. But you can, on the back end of that flue gas, you can capture additional heat with a lower temperature process. And so when you talk about condensing economizers in a steam boiler, you're usually talking about something like that. Condensing boilers are usually for hot water heating, and I do have a different presentation on that, which I actually just shared in the link. That's a great efficiency technology. And you should check out that presentation. Okay, I'll hang out for a few more minutes. Feel free to drop any more questions in the chat, and I'll address them as they come up. All right, everybody, I'm not seeing any more questions, so I think we're going to call it. But feel free to reach out to me at my email there if you ever want to discuss any Steam systems or anything we talked about. And we hope to see you on the next webinar. Thanks, everybody. Have a great week.